Look at the Strait of Hormuz during a regional conflict, and you see exactly how fragile the global energy grid really is. When tensions flare in the Middle East, the first casualty is the security of supply lines that feed energy-hungry, import-reliant nations. For a rapidly growing economy like India, this geographic vulnerability creates massive macroeconomic instability. Billions of dollars are drained annually to import fossil fuels and the enriched uranium needed to keep the grid operational. Eliminating this dependency requires establishing a completely closed, domestic nuclear fuel cycle. Global shipping bottlenecks are structural threats to national sovereignty. Solving that threat requires a systemic technological overhaul. That overhaul starts with India's ultimate strategic asset, an element called thorium. This data plots known global reserves. Roughly 25% of the planet's thorium is located inside India's borders. But there's a roadblock. Thorium is fertile, not fissile. Fire a standard neutron at a thorium nucleus, and it's deflected away. Because it is fertile, thorium cannot sustain a nuclear chain reaction on its own. Harnessing the energy in thorium requires a specific neutron environment to facilitate isotopic transmutation. This environment is created by the prototype Fast Breeder Reactor, or PFBR, located at Kalpakkam, and it recently achieved criticality. Without a breeder reactor to provide the necessary fissile driver, India's thorium reserves remain chemically inert and energetically inaccessible. To understand the origin of this strategy, we look back to the architect of India's nuclear vision, Dr. Homi Bhabha. He designed a three-stage nuclear program specifically tailored to these domestic resources. This flowchart illustrates his roadmap. Stage 1 involves pressurized heavy water reactors, which run on domestically available natural uranium. As these Stage 1 reactors burn through that uranium, they generate a specific byproduct, plutonium-239. Moving to Stage 2 requires capturing and accumulating a significant inventory of that plutonium byproduct to serve as the initial fuel. This brings us to the milestone at Kalpakkam. The central reactor vessel has officially achieved criticality, a state where the mathematical metric known as K-effective exactly equals 1. Reaching criticality means the reactor is now maintaining a sustained, independent chain reaction. Stage 1 was the ignition sequence. This Stage 2 reactor at Kalpakkam is the heavy industrial engine built to change the fuel cycle. The FBR utilizes a neutron economy that significantly alters standard fuel consumption rates. This model shows how standard thermal reactors operate. They use moderators to slow down neutrons. These slow neutrons cause fission and release energy, but leave behind depleted waste. A fast breeder operates in an unmoderated environment. It relies on neutrons traveling at extremely high velocities. When one of these high-energy neutrons collides with a fertile uranium-238 nucleus, the result is an isotopic transformation. The uranium-238 absorbs the fast neutron and decays into a completely fresh, fissile atom of plutonium-239. Engineers measure the efficiency of this process using a metric called the breeding ratio. Because the reactor produces more plutonium-239 than it consumes to maintain the reaction, its breeding ratio is greater than 1.0. It generates new fuel faster than it burns its starting supply. The FBR operates as an atomic forge, converting fertile waste into a continuous supply of energy-dense fissile capital. Scaling this transmutation up to an industrial power grid requires extreme engineering. This top-down schematic reveals the structure. At the center is the active core, an inner ring containing a mixture of plutonium and uranium where the initial fission occurs. Surrounding this core is a thick shell known as the blanket. This blanket is packed entirely with fertile uranium-238. The core is specifically designed to allow excess high-energy neutrons to escape outward. The blanket functions as a capture zone. It catches that escaping radiation, forcing the U-238 atoms to undergo transmutation and breed fresh plutonium. By directing high-energy radiation into a fertile shell, engineers have built a system that generates its own fuel supply. Once the Kalpakkam reactor has accumulated a sufficient surplus of this bred plutonium, it enables the final transition in the National Energy Plan. The reactor's configuration updates. The uranium-238 blanket is replaced with thorium-232. The process repeats. The core fires fast neutrons outward, striking the stable thorium. The thorium absorbs the neutron, transmuting into uranium-233, an efficient fissile fuel. This freshly bred uranium-233 is then extracted and used to power the next generation of advanced heavy water reactors. Loading that uranium-233 into those reactors initiates stage 3 of the nuclear program. The successful execution of the uranium to plutonium cycle provided the engineering foundation required to finally initiate the thorium fuel loop. Stepping back from the reactor physics reveals how this achievement impacts the global energy landscape. India is now only the second nation in the world, alongside Russia, operating fast breeder reactors at a commercial scale. Reaching this level of commercial scale-up is the result of the engineering work managed by Bhavini at the Kalpakkam facility. The long-term economical is clear. By closing the fuel loop domestically, the state systematically reduces reliance on imported fossil fuels and foreign uranium. Domestic control of 25% of the world's thorium reserves provides a fuel supply capable of powering the national grid for generations. Achieving criticality at Kalpakkam provides the technical mechanism for India to transition from a fuel-dependent state into a self-sustaining nuclear power.